Hello everyone and welcome to Handmade Hero, the show where we code a complete game live on stream. We have a off-topic stream today. By way of apology, I realized I did an off-topic stream yesterday because I wanted to talk a little bit about broken shaders in Unity games and for pixel art and how you would fix them if you were making a Unity game, for example, and had access to the shaders. We tried maybe to go actually fix them ourselves, but we found that NVIDIA's Nsight tool actually doesn't let us edit compiled shaders, so we aren't really able to eject our shaders without doing a little more craziness, which we didn't really want to get into. But that's what we did yesterday, and I realized that that was pretty rude to do, and I apologize because we had a standing request for ZRIZI on the chat about doing an explanation of how skinned mesh skinning works. They'd been asking for that for a while, and I was like, when we get a break, we'll do it. And then I went and did something that I wanted to talk about without even thinking about that. So I apologize. I don't think ZRIZI is with us today, but I'm sure he'll watch the VOD because he's been asking for this. So we will cover skinned meshes today, and then we'll go back to regular Handmade Hero programming next time. So first, let me say that this is kind of a nice change, which is to say that this is actually a topic that I have a ton of professional experience with. There's only so many things in a game programming career that you've really spent months of time working on particular problems. And other things you maybe have experience with, but they're not necessarily a specialty. As far as skinned meshes are concerned, I mean, I spent, 4 to 5 years at Rad Game Tools literally just doing skinned mesh character animation technology, both the export side and the runtime side. So it's something that I have a lot of experience doing. And so I am happy to go into how it all works, because I feel like, unlike some topics where I have to give a disclaimer where I'm like, I don't really know that much about this, so you should probably go take a look at an expert's thing. In this case, I think I can probably give you a pretty complete explanation of at least the initial set. Now, one of the things that you have to remember about 3D mesh skinning is there's a set of core things that you have to understand about it, and that's what we'll go over today. And then there's a lot of things on top of it that you may or may not want to be aware of, depending on what your goals are and what you're actually trying to accomplish with it. Are you Pixar? Are you trying to give character animators a lot of stuff to work with that has to do with pose and traditional animation techniques, that sort of thing? Do you have an infinite amount of time? Well, not infinite amount of time, but do you have a substantial amount of time to render a given frame? So you're thinking about things beyond just the things that can happen at 60 frames a second. So we'll try to mention what some of those technologies are, with the caveat that they are changing all the time. So every year, I mean, this is what SIGGRAPH and stuff and Eurographics oftentimes are focused on in their character animation mesh skinning papers. They are new advances trying to make better tools for doing this sort of stuff. And so we will cover today all the core stuff that you will need to know to get yourself started on character animation with mesh skinning. And then you will have to decide where you want to go from there, because there's no way to give a complete description of all the rest of it, because not only is it changing all the time, but there are many different paths you might go down. So as you might expect, this is going to be a very Blackboard heavy episode, so let's just dive in and talk about it. So here we are. This is introduction to mesh skinning. And I'm going to talk primarily about 3D mesh skinning, but 3D mesh skinning is sort of a superset of 2D sprite skinning. And so if you know how to do 3D mesh skinning, you also know how to do 2D sprite skinning. So if you are someone who wants to learn how to make like bone-based models for 2D graphics that allow them to warp around, you can also use all the same things I'm talking about here for that by just eliminating Z. Literally, there isn't really anything else to it. There are some specific things you care about when you're doing 2D mesh skinning that maybe you don't need to know as much about for 3D mesh skinning that are like specific to how things maybe like overlap in sprite space, because if you're not doing real 3D, you might not know some of those things. But for the most part, all of the math is the same. All right, so let's start with the basis for 3D graphics that everyone has learned or should have learned before they come to this introduction, because I've got to start somewhere. So if we're talking about introduction to mesh skinning, I'm assuming that you understand a basic transform, okay? Now, a basic transform is something that's like intro in any 3D thing. We've covered it on Handmade Hero, so you can go look at it if you want to know about it by using the search tools on handmadehero.org/watch. And so I expect you'll know what I'm talking about. When I draw like a coordinate frame like this, oops, see you going up there. When I draw a coordinate frame like this and say that we can write a transform that takes a basic coordinate system like this one from some orientation that is considered a rest pose or a neutral modeling pose, around which we build something, some kind of a shape, right? Built out of vertices and triangles, or really whatever you want, as long as there are points involved that we can talk about in this space. I expect that you'll understand what I mean when we say we have a transform that can go from here, this coordinate system, to this coordinate system, right? And so you expect to be able to transform the coordinate system and have all of the points go with it. And we've done this on Handmade Hero, and again, we typically write these as matrices, so you might see me write oftentimes on Handmade Hero that like a new point, right, which is a point in this space, is equal to whatever the point was in this space times some matrix which is in the way, right? This matrix, T, transforms these points in this order to, the new points that you're going to use. And you see us do this on Handmade Hero all the time. And again, there's nothing magical about a matrix. And I just want to underscore that again. They're not magical. You don't have to treat them like a black box. In fact, there's an entire there's an entire lecture on my website, How to Open a Black Box, that talks about why you don't have to think of matrices as a black box. But these matrices are just vector components, or, they're numbers we understand. If you look at a matrix, right, typically they're 4 by 4. And if you look at a matrix, you can read off the components by breaking them into some structured things, the ones we typically look at. They typically look like this. And what you'll see is the first 3 components going down, right, in the first column of the matrix. This is the new x-axis. So this vector here goes here. This vector here goes here. And this vector here goes here. Okay? The location of the origin, so where the vectors emanate from, which is normally 0, 0, 0 in the resting position. I will often refer to this as the resting position because we need something to differentiate this origin from the one that we're actually drawing. So we have the rest position and then sort of like the drawing position. Sometimes this is called like world space, right? Where I'm trying to put the thing, but it doesn't have to be world space. It could be anything we're doing. We have some sort of source, which is the rest, and then we have some destination, which is whatever we're actually generating. Anyway, this point in space goes here, and then the bottom is 0, 0, 0, 1. Now, if you don't understand why this is, again, it's a very simple homogeneous transform. I shouldn't have put P there. This is like the origin, so let me just put like O or something for origin. I don't know, because I was using P for the point, so I apologize. I'm bad with math naming. I never pick good letters. And again, a simple just review of how matrices work. If in here we're talking about some kind of transform and I have some source point, which I'm calling P here. I have a PX, PY, PZ, and then traditionally we put a 1 in here. That's for using what are called homogeneous coordinates or 4x4 matrices where you're encoding only 3 dimensions. That extra dimension is to allow you to do that affine movement, to allow you to move things around. Again, outside the scope of this, I just want to make sure you understand all this. If you don't understand anything, any particular part of this doesn't ring a bell to you, you should go back to some of the episodes in Handmade here where we talk about it, or go to look at your favorite introductory 3D textbook. They will cover this. This is just the basic stuff. So this is all stuff you need to already be familiar with. But anyway, point being, when points come in here, the way they multiply these out is very straightforward. If you do the matrix math, you will see that px multiplies the x coordinate, so you end up with pxx, plus py multiplies the y, py, pz multiplies the z, and the origin just gets added on because it multiplies this, right? So this is the, I don't know, position of the origin. I need to give it some name that stands out. I don't know. It's bad to say PO. I don't know what to tell you. We'll figure out some better names later. You should just understand this. Basic transform. It's very, very simple. The elements of the vector multiply the elements in the matrix such that they pull through these axes, right? X, Y, and Z. And you can see exactly what this is doing. I'm going px along the x-axis. I'm doing py along the y-axis. I'm doing pz along the z-axis. And so wherever I had worked myself out to before in the rest position, I am working myself out to the same exact position, just in a new coordinate frame that's been placed somewhere in the world. Very, very straightforward when you think about it in terms of these components. Get yourself comfortable with this by either reading up on it or watching old episodes of Handmade Hero, because that is the, one major part of what we need to talk about today. So you need to be comfortable with it. Get comfortable with it. Now, the other thing you need to be comfortable with is the linear blend. And I said on Handmade Hero, I think I said at some point, let me go with the box there. I think I said at Handmade Hero at one point, there's sort of like this concept of desert island code. Like, you know how they always say, like, you're gonna stuck on a desert island, like, which 3 albums do you take with you to listen to? Because you gotta pick, like, the 3 you're gonna really rely on. So if you had to take 3, pieces of code with you to a desert island or something, I don't know, 3 pieces of math, let's say, the linear blend is kind of one that I think should make the top 3 for any game programmer, because it's such a cornerstone operation. Matrix transform for points is probably another one. So you're talking about 2 of the big ones here. They are heavily leaned on to do mesh skinning. So linear blend, you got to be comfortable with it. What is it? Well, a linear blend is just a way of saying, one of 2 ways of thinking about it, and I'll show you both of them. They're very simple. The one we typically encounter most often is the concept of a ramp between 2 values, essentially. And so, for example, I might have a t parameter, right, which is the blend amount. And it ranges from 0 to 1 inclusive. So it can be 0, it can be 1, or it can be any floating point number in between those 2. And then we write the equation 1 minus t times some value plus t times some other value equals the blended version, right? And so, this is maybe a point or something, whatever we're blending. I don't know what these are. They could be anything, literally anything that admits a linear combination. So points, matrices, pixels, whatever you want. This equation is a thing that goes from A to B as t goes from 0 to 1. So if these were points in space and this was A and this was B, then if t is equal to 0, you have 1 minus t, which is 1, times A, so that's just A, plus 0 times B, which means I've gone nowhere. I've just stayed at A. If I put 1 into the equation, I have 1 minus 1, which is 0, right? So no A, plus 1 times B, which is just B. So at 1, I'm at B. And anywhere in between, I am a combination of the 2. So 0.5, 0.5, if t is 0.5, I get 0.5 here and 0.5 here. I'm right in the middle. If t is 0.25, I get 0.75 here, which means I'm about that close to A, 0.25 here, right? So by setting t to some proportion, I get a linear movement between these 2 points or to anything. Colors, doesn't matter. All right. So these 2 fundamental concepts to graphics programming in general, the basic transform of things in 3D space by using 4x4 matrices, or if you didn't want to use matrices, even just this equation. The idea that we have 3 axes, x, y, and z, that describe an orientation in space, and then some basis to put them around, like a point in space that forms the new origin. And then we're taking input points in some source space and reinterpreting them to move them. This equation and this equation are core. Now, I said there's 2 ways to think about this, and this is by moving to the second way of thinking of a linear blend. That's how we'll sort of start ourselves into our mesh skinning topic. Okay. So another way to think of a linear blend is to think of it as something that doesn't just involve a single scalar value that moves me between 2 things. Okay? So what I'd like to introduce today is the notion of convex linear blending. Now, what I mean by convex linear blending is I mean to say that rather than thinking about a t value that ranges from 0 to 1, and that gives us a way of moving between 2 points, A and B, I'd like to talk about the concept that for any collection of things, we can create an equation that always gives us something that that will result in a answer, a blend, that is inside the set of inputs we give it, right? So if you think about that original linear blend, 1 minus t times a plus, t times b, and we think about what these points are, and maybe, let me start to write this a little more formally so that we can kind of get, I can try to rectify my problem from earlier I was talking about where I always name things poorly. Let's say that we've got p0, 1 minus t times p0, and then I want to add p1, and then I want to get my p prime, which is the resulting point. Let's actually start to talk about the math, try to be a little bit more specific about it, because this is supposed to be giving you the fundamental basis you can use to understand these things. This is the same equation we wrote before. If I drew it out, I would have p0 here, right? I would have p1 here, and then this line between them is everywhere that p prime could appear by setting t equal to something between 0 and 1, right? Now, it's crucial to understand that this already creates a convex linear blend. We have created a convex region. We have created an enclosed region. It happens to have no area, but it is a line. And no matter what we do, we will never move outside of it. t0 to 1 will always produce a point that's inside of it. Now we can, and oftentimes, again, we will call this interpolation. Right? You hear that? Interpolated, interpolation. Why? Because we are inside the 2 sample points that we're given. We're given p0 and p1. We are interpolating, right? Now we could extrapolate, right? This is totally possible. How would we do it? Like this. Oh, that's the worst infinity sign I've ever drawn. No, it's not. Probably drawn a worse one. By letting t range from negative infinity to infinity, right, giving it the entire range, it can do anything it wants, we would start to move beyond these 2 points, but still along the line. So rather than a convex linear blend or an interpolated linear blend, we are creating something that allows us to go outside of our sample point, right? We are creating something that is not contained within the shape originally implied, in this case, a line segment between our points. Right? So if, for example, I set it to -1, I would end up with something that was out here at negative, like whatever this vector is that you want to call p1 minus p0, I would end up with the negative version of that vector taking me out to the blend. If I let's give this a name. Let's call this our f of t, right? Our f of -1 is all the way out here. at the negative of that vector. Because if 1 moves me to here, -1 moves me to here, because it is linear motion, so we expect it to always move the same distance for any size of t that is equal. If I move it +2, I expect it to move the same distance as -2, right? If I go from 0.5 to 1, that should be the same distance as 0 to 0.5. Because as long as I go the same distance in t, I should go the same distance in space. And that is why we say linear blending, right? That's the linear in linear blending. If this were nonlinear, if there were squared terms in here, if t appeared as a power other than just linear, right, just to the first, then it would be a nonlinear blend, right? It would be a blend that does not move the same amount for a linear change in t. Linear changes in t produce linear changes in space. Nonlinear changes in t would produce nonlinear changes in space, but that we wouldn't call that nonlinear blending really, because again, the blend is still linear. We're nonlinearly changing t, right? But just to point out, there is such a thing as nonlinear blending, and that is when these values appear squared or cubed or any other power in the blend equation itself, because then a linear change in t translates into a nonlinear change in space. Hopefully that makes some clear sense to you. Okay, so what I'd like to do is introduce the concept of the convex linear blend as a more general form of this equation, and that will get us into mesh skinning. If I wanted to look at this more broadly, I could say, well, you know, what is this actually doing? Where did I get this notion of 1 minus t plus t? And could I think of that more broadly? And the answer obviously is yes. If I just start to think of this as a sum of terms, where those terms have certain constraints, I can start to form a more universal way of thinking of a convex linear blend, where I can get more interesting results, more power out of the same idea without doing any more work, okay? So what does this actually amount to? Let me rewrite this equation as C0, which is going to be equal to 1 minus t, and C1, which is going to be equal to t. What does that make this equation? Well, 1 minus t is just C0, so that's times P0, plus t is just C1, so I have P1 here, and then I get my result, right? C0 P0 plus C1 P1 equals P prime, okay? Same exact equation. All I have done is replace these terms with different names. I just named them something else. I said C0 is 1 minus t, C1 is t. Same equation, does the same thing. I input some value t, I produce these two results, and I get my blend. Now, why would I want to do that? Well, hopefully you can see the obvious step coming next. What if I just said, well, forget this. Let's just talk about arbitrary numbers I can multiply by P0 and P1 to equal P prime. Suppose I didn't know about 1 minus t and t in the first place, right? Suppose I didn't know. Well, if I said I wanted to produce some kind of equation where C0 and C1 multiplied P0 and P1 in such a way that they produced a point, like I was doing, and I didn't know about 1 minus t and t as being the magic way to set them so that I always got things in between them, right? So P prime, here's P0, here's P1, right? What would I have done to figure that out, right? Like, how would I have figured out that that's what I wanted to do, right? What was it that was guiding me to produce this t1 minus t thing in the first place? And if we understood that deeper idea, would we be able to produce something more powerful than the simple version that just moves us between the 2 points, right? And so the answer is that these right here actually come from a more systemic way of looking at these components in a summed vector equation like this. It comes specifically from a thing called norms, which I've talked about on Handmade Hero before. And what norms are is they're a way of looking at a series of parameters such that you get certain results out of them when, or it's certain ways of measuring them and certain ways of unifying them with those measurements, right? And so let's talk about one you actually know, probably intuitively already, and then one you might not actually know. You've probably seen it before, but maybe you haven't thought about it. On Handmade Hero, if you've watched the whole thing, then you do know about these because I've already talked about them. But we'll kind of ease into it because people probably will watch this stream standalone as opposed to as part of the series. Okay, so let's talk about Euclidean norms. So what we've got when we talk about vectors in space, right, in a standard coordinate system that's Euclidean, which is pretty much all we use in basic graphics, right? 3D, 2D. When you're not talking about solves or rotations and stuff like that, you're typically talking about Euclidean spaces for points in 3D space. What we tend to do is we tend to always just have known from when we started the concept that, we've got some vectors, like I've got a vector here and, I've got some point or something. So I've got a vector, say v, and that vector... well, actually, you know what? Let's call it something else. I've got a vector A, and that vector in space goes from the origin to some location, typically is what way we think about it as a displacement or something. But we also can talk about the vector as itself pretty simply by saying things like it has a length, right? Like my vector A actually has a length, which is typically written like this, and that length is the distance along the line you would have to go if you were walking in that direction and you wanted to go from the origin to the endpoint, right? There's like a distance here, right? And this length is equal to that distance, okay? Now, we think of those as distance, the length of the vector, that sort of thing, but it's really actually computed, obviously by the Pythagorean theorem, which you all know, which is ax squared plus ay squared square rooted, right, is going to be equal to this distance, right, the d. And why is that the case? Well, it's the Pythagorean theorem right here. We know that ax is this. We know that ay is this. We know the Pythagorean theorem says that ax squared plus ay squared equals whatever you want to call it, length of a squared. There you go. So if I want to know my length of A, let me write that as length of A. If I want to know my length of A, we square root this term here, and we get the familiar equation that everyone knows for the length of a vector. But this length of a vector, even though I don't know that Pythagoras probably knew about it because he was sort of blazing a trail, so I feel like norms kind of got introduced afterward. The Euclidean 2 norm is actually this. This equation here, the ax squared plus ay squared square rooted, is actually something called the Euclidean 2 norm. 2 norm is what we call it when we square each term and then square root it. The 2 is the square and square root, and I can write the concept of a norm more directly as saying that my norm of the power, I don't know, I don't want to use p, norm of, it's going to be a theme, I'm bad at naming them, norm of n, let's say. Well, that's even worse. God, I hate naming things. Norm of g, I don't know. Norm of g. So the Euclidean norm for some number is just equal to the sum of all of your terms in the vector, so however long it is, right? If I have two-dimensional, it's 2. It's equal to the gth root of each of those raised to the g power. And this goes on for however many terms of vector you have. If I have ax, ay, az, aw, blah, 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 right? These would all appear here to the g power, summed, g rooted, okay? The 2 norm is the one we're most familiar with intuitively because it is the length of the vector. And what the 2 norm does is it tells you how long the vector is if you went along it, the hypotenuse of this triangle. But there's another norm. There's in fact an infinite number of norms, anything you plug in here. So norm 2 is the length of the vector. But norm 1, what is that? Well, we know how to produce it, right? Norm 1 is a 1th root, which is nothing, right? That just goes away. And then everything to the 1th power, first power, and that goes away. So if I take ax to the 1 plus ay to the 1, 1 rooted, what do I get? Well, I just get ax plus ay, right? And that's it. Now, if you were a math pedant, which I'm not, I wish I was, it's handy to know a lot of math, you would probably know whether or not these are traditionally absolute valued or not. I want to say that they are. So I want to say that traditionally the norm is written like this. So the 1th power removes the sign. But I don't really know that that's true. So I'm not going to state that strongly here one way or the other. That's for math people to know. So I'm going to say that they aren't right now because the 1th power itself doesn't necessarily imply that. So let's just say for now that the 1 norm doesn't do that. But I would encourage you to talk to a more math person. I would encourage you to go look up the math there if you want to know the actual real answer. For our purposes, it won't matter because we want to just be able to understand both, whichever one we want. If that makes sense. Okay. So, coming back to what we wanted to know here, well, we've got ax plus ay is the Euclidean 1 norm. We know that the 2 norm tells us this, right? The length of a. What does the 1 norm tell us? Well, what is ax plus ay? It's walking out this far and then walking out this far. It's the route along the outside of the triangle formed, right? So the 2 norm gives us this. The 1 norm gives us this entire distance. It's the Manhattan distance, as we sometimes call it. Of the vector, right? So, we've got this is as the crow flies. You could say, if I had to write, norm of 1 is the Manhattan distance. Norm of 2 is the crow distance, right? So using these 2 norms, we can actually think in a more systemic way about which of these things we want to talk about. We can calculate the crow's flies distance by doing norm 2. We can do the Manhattan distance by doing norm 1, because it's just the sum of the sides, right? If that makes sense. Okay, so why did I want to go down that digression? Well, it wasn't a digression. It was how we explain this. In order to produce the original 1 minus t blend equation, what we were trying to do here, right, is we were trying to make it so that we always produced values that lie between p0 and p1. And by taking the Euclidean 1 norm of the weights, if you will, of the coefficients on p0 and p1, we were essentially trying to say, how do we produce a coherent equation that allows us to always produce a convex blend between them? And let me show you how that works. So, if you want to make sure that your Manhattan distance is 1, right? If I want to make sure that I've always got a distance of 1 when I go along the length of my vector, again, we all have learned how to do this from working on our 3D stuff. We know that if we take the crow's flies distance, right? If we take the length of the vector, we can always divide the vector by that value and get a unit vector, right? We know this, we do it all the time. Why does that work? Because this has a length of whatever the length is, right? This has a length of the length of A. This is the length of A. If I divide something with a length of A by the length of A, I get a length of 1, right? It's because vector math distributes to its components. So if each of the components get multiplied by something, that's exactly how much less you get in the squared sum, right? So normalization to the 2 norm, we know what will happen. The 2 norm dividing by the 2 norm produces a 2 norm of 1. Because, what a surprise, you divide the components by whatever the 2 norm value is, you get a 2 norm of 1 out the other end. The same is true of dividing by the 1 norm. A over the 2 norm, maybe I'll write that like this, norm 2 of A, so I can pass A in. So norm 2 of A, right, over A, this equals a unit vector. But A over the 1 norm, right, that equals a sum of 1, right? It's just this before was Pythagorean's theorem sum to 1, right? At rooted equals 1. This here is just the term sum to 1. So this means ax plus ay dot dot dot, however many you have, I guess, equals 1, right? It allows me to make all of these things sum to 1. And how do I do that? Well, exactly the same way I did it here, right? I compute the norm and then I divide the components of A by that norm. Again, super simple. It means I take A and divide it by ax plus ay plus however many components it has, right? So this is just a long-winded mathematical way of introducing you to all of these concepts that are helpful to kind of know where they come from, but it comes back down to understanding where this basic idea came from. It was the 1 norm. How did I get this? Let's look at it now and start to pull it apart. Okay, so I am wondering how one might arrive at these. Well, if I was to just say that I have a vector, right, of these, a vector C, and its components are C0 and C1. So I'm talking about the 2 weights I'm going to use in the equation here. Oops. So I'm talking about this, where I've got, C0 and C1. And I want to know, what would I do, if I wanted to produce a version of this equation that's always going to give me something in between P0 and P1, right? So it should always lie along this line, okay? Well, if I was to take the 1 norm of C0 and C1, right? If I was to take the 1 norm of this vector, so norm 1 of C, what would I get, right? I would get C0 plus C1, right? That's the 1 norm. So if I just had any 2 values that I placed in here, who knows what they were? They were something. I don't know what they were. They were any values you gave me for C0 and C1. And I wanted to turn it into something that fell into the convex 1. Let's do a 1 normalization on it, right? Let's do the 1 normalization on it. That means I divide C by the 1 norm. This is the 1 norm. I'm dividing C by the 1 norm. What will I get? Well, I'll get C0 over C0 plus C1, right? And C1 over C0 plus C1. I mean, that's the new vector, right? And what do I know about this new vector? I know that it always has to sum to 1. You can see this trivially by inspection. If I add these 2 terms together, not knowing what their components are or anything else about them, you can see that they both have the same denominator, so they would add directly on top, and C0 plus C1 over C0 plus C1 is 1, right? So we know that that actually happens, okay? So now what we could say is, look, if we wanted to simplify these equations down a little bit and say, how would we write one in terms of the other? All right, we've got a puss situation. Molly Bean, Molly, no, we're right in the middle. We're right in the middle of a Blackboard session, baby. You gotta wait a little bit. All right, I think the puss wants to play, but we're gonna have to finish what we're doing here first. Okay, so if we know that these things sum to 1, right? And by the way, if we look at what happens here, if we look at what we were talking about with our original blend equation, what's the 1 norm of these? Well, 1 minus t plus t, right, is just 1 minus t plus t. The t's cancel and you get 1, right? So you can see already that 1 minus t and t satisfy the one norm equation already, right? They are a simplified version of that. But if we wanted to try and get these values more simplified, let's see how we might do it. And again, I'm always a little weak on the math, so you'll have to forgive me if I fumble a little bit. No matter how much I work with this stuff, it always falls out a little bit. But anyway, so C0 over C0 plus C1, and C1 plus C0 over C. So let's say I wanted to create some new equations here that are just based on these. C0 over C0 plus C1. C1 over C0 plus C1, right? So if we took a look at these equations here, right, and we were to say, all right, I'm trying to make some new versions, and what I want to do is I want to rewrite this so that it's only in terms of one variable, right? I want to create something that satisfies these properties, but such that I won't ever actually have to put in two random values and then do the simplification, right? So if I was to do some multiplication out on these guys here, actually, I don't know if this is really going to work. I may skip that part because I probably would have to think about how to do the substitution, and I don't want to get bogged down in that yet. So suffice to say, if I was more on top of my math game right now, I would probably be able to show you how you easily do the substitutions that reproduce the 1 minus t here to get to here, as opposed to just pointing out the fact that obviously this is the simplification of these equations that produce one variable which always results in something pre-set up for normalizing to the one norm, right? But you can see that behavior in the 1 minus tt, and that is the crucial property of these equations that actually make it always stay inside where it actually started, the p0, p1. It is specifically the norm 1 of these c values. It is the fact that they are normalized to the one norm that keeps them inside between p0 and p1. Now, why does that happen? Like, what is it that makes what is it that makes the one norm special as far as summing things together? Well, if you think about a slight change of basis, I can give you a more intuitive understanding of why that works. Let's suppose that the origin was here, right? So p0 is that vector, and p1 is that vector, and the origin is right in the middle, right? Well, what do I know about the space that I can span using these two displacements, right? Well, if I was to assign any particular values to C0 and C1, what I know is that they always have to sum to 1, right? So I can never get a value, I could never get a vector larger than, say, this or this, because I can never make more than 1 multiply P0 or P1. Right? So I head in this direction, I can only ever get out to P0 because I can't set it greater to 1 or I'd violate the one norm just with P0, right? And when I'm heading out in this direction, I can never set P1's coefficient to anything higher than 1 because I'd violate the one norm there as well, right? And again, I should say I'm talking a little bit more about the absolute value version of the one norm because technically I could set the weights on C0 to something negative, which would offset the amount of P1 and so on, right? So let's, I don't really want to talk about weights that are negative just yet. So let's keep, for our intuition, these are just positive coefficients for right now, but we can talk about negative ones a little bit later. All right, so I can't really ever get out of this cage, right, from where I start, because I can never get further away. Now you may ask, well, what if the origin was over here, right? And so P0 is there, like, and P1 is here. Why can't I get, somewhere that's closer in? Why does it always stay on this line, right? And the answer is because every time I try to detract, to get backwards from P1, I have to add the equivalent extra amount of P0 in to sum to 1, which means that I'm always gradually getting closer to P0 as I go. Since I know this is a linear equation, it can't bow in because that would be a curve. So the only way to go directly from P0 to P1 if the weights can never dip below 1 is a sum, and I know that 1 puts me here for C0 and C1 of 1 puts me here, right? There's no other route it can take. A linear equation can't take another route because it's linear, so I can't curve. And so the only thing that makes me smoothly go between those two, if I force the weights to sum to 1, has to be a line. So I know that I'm stuck between my 2 points. I can't get inside, I can't get outside, specifically because I have constrained these 2 values to always sum to 1. And that is the constraint of the 1 norm. This is the simplified version of the equation, but I can just use this equation where I just do this equation, where I just put in any 2 values I want, and then I normalize them by their sum, okay? All right. Hopefully that made some sense. I never know when I'm talking if I'm making any sense to anybody, because these are just the way I think about things. They may not be ways that make sense to you, so I apologize. So now let's talk about the multi-point blend. This is the foundation of mesh skinning. So hopefully you will understand why I had to motivate it by talking about all of these sort of 1 norms, blends, blah, 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 right? Multi-point blending is the idea that I may want a lot more points. P0, P1, P2, P3. What am I doing going clockwise? Who goes clockwise? Let's go counterclockwise. All right. If I was to set up some arbitrary number of points, in this case I've done a pentagon, but it could be any number of points. If I want to create a multi-point blend, and I want to know that it is a convex multi-point blend, meaning I stay within the boundaries that I am provided, right? I can apply the same thing we just did for 2 points to any number of points, right? And all the same thing applies. So if I want to extend my notion of those coefficients out to 5, I just have 5 values in my coefficient vector for my 5 points, right? I have C0, P0, plus C1, P1, dot, 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 to C4, P4, right? And all I have to do to ensure that I stay inside, where I'm going here, is to make sure that these values sum to 1, because the exact same thing applies. No matter where the origin is, if I equal 1 on any of these points, I'm at the point, right? I know that because everybody else has to be 0. That's the requirement of sum to 1. So if I'm doing this, right? If I've divided all of my weights by their sum, by their 1 norm, right? If I've divided all the weights by the 1 norm, I know that if any one of these values is 1, the rest have to be 0. So I'm going to definitely be at one of my points. And any minute change has to increase my motion towards one of the other points. Because if I was to ever decrease my contribution to P0, I must put that contribution towards some other point, right? It has to go towards it. Because I can't drop any of these values negative. Like I was saying before, I'm enforcing absolute value here. Not absolute value, I'm enforcing greater than 0 here for purposes of our discussion. So I have to move towards, say, P1, or I have to move towards P3, or a combination of P3 and P2, right? But I can't ever regress away from the shape that I've created. Everything I do must stay inside it. Hopefully that makes some intuitive sense to you now after we've looked at it a little bit more. So this means we can now form our general blend equation, which is very simple, very, very simple. Now that you've seen the underlying parts of it. All we really have to do is say that we have some set of coefficients that we're going to multiply some set of inputs by, and that is pretty much the end of the story, right? So let's write this out in the way that we tend to do it in mesh skinning, and then I can show you the mesh skinning equations. So typically what we do is we say we have a weight vector. Now, coefficient I think is better. I would probably prefer to have used C for this, like I did above. I think it makes more sense with the math, and it also unifies it a little bit more with B-spline blending and stuff like that, where typically you think of the knot weights as being a vector of C. But just to give you some familiarity with how they're often written in the literature and how often we talk about them in game programming, I will say that a weight vector, which is our C vector from before, is oftentimes written as W's. And you saw me kind of introduce that briefly up above. So I don't care which letter you use. I'll start using W now. We used C before. I'm going to use those interchangeably because you kind of want to know both. If you're in spline land and doing nonlinear interpolation, you see this. If you're in matrix multiply linear weighting land, you tend to see W. You need to just know both of them are used for weights. There's not a lot of science to it. That's just what happens. All right. So you can either think of it, as C equals C0, C1, C2, C3, ba ba ba. Or you can think of it as W equals W0, W1, W2, W3. They're just two names for the same thing. A vector of coefficients we're going to use for a blend of some kind. Right? So what we have in the basic introduction blending equations is just our final point is always equal to W0 times P0 plus W1 times P1 plus ... plus Wn times Pn for any number of inputs. That gives us a set of P's, right? So we have our set of points, that's our P. Pn equals our set of points, right? And we have Wn equals our set of weights. These are the fundamental concepts of blending. Extremely straightforward. A set of scalar numbers, 0.5, 0.2, 0.2, whatever, 0.1, and a set of input points. These input points can represent anything linearly combinable. They can be vectors, points, colors, I don't care. It can be anything, right? Anything that emits a linear combination, as written here, where I can multiply them by a value and then sum. So FMAD, right? A floating point multiply addition. If you can do that with this thing, then we're in business, okay? And this is the fundamental equation for blending you should always be familiar with and always mapping things back to in your head as we talk about mesh skinning, which is going to be really anticlimactic now because we've basically covered the entire thing. I know it sounds a little bit weird, but that's actually it. If you understand this and you understand the Euclidean one-norm normalization that allows us to produce a Wn that is always convex, you pretty much know mesh skinning, and I'm not going to have to tell you very much going forwards. So what is mesh skinning? Well, mesh skinning was an attempt to solve a problem. And the problem is, what do you do if you don't want your objects to be disjoint when you transform them? All right, so let's suppose I wanted to make an arm, and I want an elbow, and I want it to bend. Well, in early computer graphics, all we could do, right, and I'll draw this in 2D, but it works the same in 3D, is something like this. Here's the upper arm. Here's the forearm. And you know the hand would be out here somewhere. And this is the elbow joint. Now it's 3D graphics. I already said at the beginning, you should be comfortable with a basic transform. We know what these basic transforms are, right? We can create a bone structure and basically say, hey, there's a coordinate system right here. There's another coordinate system right here. And we just transform the upper arm geometry by this transform. We'll call that T0. And we multiply this one. Actually, let's call it B for bone. We'll call this B0, right? And we'll call this, no. You know, I'm going to call it T0. We'll call this T0, right? Transform it. And we'll call this T1, right? We'll transform the forearm by that. And that's our final shapes, right? It's the non-mesh skinning version. It's the non-mesh skinning version. And there's a big old gap that forms at the elbow because these are two disjoint shapes. As they get transformed, they separate even if at the beginning I modeled them together, right, like this. Then when this rotates up, you can see that a gap forms here and a interpenetration forms here, right? So what I wanted to have happen back in the old days when this was a problem, what you wanted to have happen was to have the mesh be continuous through that elbow joint, right? So what I wanted to do was, when I was doing this, what I wanted to do was just have this be one mesh, right? I didn't want there to be a separation here. I wanted these vertices to be shared, right? So what I could do at the start is something a little bit simpler than mesh skinning. What I could do is say, well, I don't really have to separate these geometrically. I could just assign these two vertices as part of the upper arm and just reuse the vertices. As part of the lower arm or upper arm. My choice, really. But I could reuse them in both sides. So when I draw the upper arm geometry and the lower arm geometry, right, I can just share these vertices. And then what will happen is there's no gap. When this starts to bend upward like this, I just, whichever one I assigned it to, let's say I assigned it here, right? Here's where they would have transformed under each transform. Let's say I picked this one, right? So these are both there and there. I now just draw this as my mesh, right? Easy peasy. That prevents the gap from forming. But if you look at what happens here, this, as this arm straightens out, collapses entirely, right? So my mesh now gets this super collapsed arm, right? Can you see what I'm talking about here? Because if we just map this to one or the other, as I start here, right? Let's look at the two cases. So one case is I get that, right? So my mesh now becomes this, right? There's my elbow. Not a very good looking elbow, right? That's if I assigned them to the upper arm, or the lower arm, rather, sorry. And if I do the opposite, if I assign them this way, then I get this. Right? Still really, really bad. So I get the same pinch, I just decide where it goes. Not really acceptable for animation purposes, right? Okay, so there are two ways of addressing this problem, and they both are actually equivalent. There's actually an infinite number of ways to address this problem, but there are two core ways that end up addressing this problem from the basic set of equations. Okay. What we want is some way of producing a more subtle blend between these two. Because if we were to look at the two superpositions here, or rather if we were to look at a superposition of these two sets, right? And let me try, this is going to be a little bit difficult. Let me try to draw the overlay for you of the two of these. Here is my coordinate system. Here is my bone structure. Here is one of my meshes that I could have. Here is the other one I could have, right? Then if we were to look at what we have produced after our blend, we know after our transforming of all of the points in all of the systems, right? We know we've got this part of the mesh covered. We know we've got this part of the mesh covered. So the question is just, how do we produce 2 points here that aren't awful? This is not good, and this is not good either. But what about some combination of these? And the answer is, if we were to maybe take this, right? Maybe we could produce something that wasn't quite so bad, right? This ends up being a pretty reasonable elbow. It bows in a little bit, right? More than we might want, but so does your elbow to a certain extent. Not really, though. The fat kind of usually bulges out here, but that is much better than that, which was almost collapsed, or equivalently the other version, which was that, right? I may have connected those wrong. But point being, this is a more preferable result. It's still not perfect, and we'll talk about what would be perfect later on when we talk about sort of the next steps after basic mesh skinning. That would be nice, right? It would be acceptable and usable, as opposed to the other one, which is not. Can you see from the diagram where I'm going with this? What is this line here between these two, right? Does it look familiar? Does it look like something we maybe just talked about? It sure does, right? It looks a heck of a lot like this original equation, doesn't it? Where these are constrained to be normalized to the one norm, right? That's that line, right? I mean, you can see it. You can see it coming out, can't you? Before I even show you. I mean, you can see that that's where we're going. So let's do it. What do we need to do to make that happen? Well, previously, right, when we transform stuff in computer graphics, I told you this at the beginning of the stream, right? We've got some transform that we're going to transform these things by. Oops, that's not a P1, that's a P prime. To produce our point, and we're inputting the point, right? So that's what we normally do. That's how we would have produced these positions, and that's how we would have produced these positions with just normal, regular, old school computer graphics where you just have one transform that moves all your points, right? And specifically in this case, we have sort of two P primes we were talking about potentially having, depending on where we assigned our points. Did we assign the points the upper arm? Did we assign the lower arm? So we have a P prime, let's say upper arm, right? And that's the transform of the upper arm times P0. But we could also do an equivalent transform for the lower arm, P prime lower, and that's just going to be the lower transform times P0, right? Not particularly complicated. I lower arm probably bad. Let's call it forearm because you can't tell the difference between 1 and an L. Right? So these two transforms are transforms we already know. We already know how to transform some point. Let's say P0 in our example here, was this point here, right? So we're talking about it transforming to either here or here, depending on which one we assign it to. If we assign it to the transform upper arm, it's going to be here, right? So this is transform upper arm times P0. If we assign it to the lower arm, it's going to be here. So this is transform forearm equal P0, right? So, we know we can produce these 2 points. They're just the basic transforms we would have gotten if we treated everything as rigid, right? Make sense? So if you look at these 2 equations, what do you think I'm going to do, right? Well, I just said, look at that line in between them. Doesn't it look like this? And the answer is, let's just use that equation. Let's take our 2 transform points, right, which are here and here, and let's just produce a blend between them. Let's just blend between them. Let's just do W0 times P prime U, right, plus W1 times P prime F. That's our new final P prime. This right here gives us 2 control levers to dial to give us any point that we want. And if we don't want it wandering all around in here, right, So if I want to know, like I don't want it out there or in here, right? I want it to be right there, let's say in the middle. Then I know I can just enforce the Euclidean 1 norm on these two, and I will get something on this line. If I literally use 0.5, then it would be 0.5 and 0.5, because that's what sums to 1. And I will literally get that center point that I drew that is what I wanted. That's mesh skinning. End of story, actually. That's pretty much all there is to it, to be completely honest with you. It really doesn't get much more complicated than that. Now, there's a ton of advanced topics we can go into, which we will in a second. I just want to cement this home. But this is mesh skinning. That's all it is. All it is weights that multiply transforms of things that get transformed in the space of more than one transform. So you're taking the same point in your input, you're transforming it by more than one of your bones inside the character, and then you're just performing a weighted convex blend, and we're going to talk about non-convex blends in a second, but a weighted convex blend between the two. Let's make this a little bit more concrete by talking about the entire process as it traditionally occurs. Traditionally, what happens is you create some humanoid shape. Some kind of gingerbread man, right? We call this the rest pose. Somebody models this in like 3D Studio or Maya or something, right? And they then create a skeleton, we call it. And that is nothing more than a series of transforms that line up with where you would typically put, the bones or the joints of a human, right? This guy should have some longer legs, probably, right? The skeleton is a set of transforms, right? Each one of these is a transform. And we compute what those transforms are the way we would compute any other transforms in 3D graphics. They have nothing to do with mesh skinning, right? So they are just a series of T0, T1, T2, ... Tn. Each of these, T0, T1, T2, whatever, right? We have a skeleton, which is a series of transforms, and then we have a mesh. And that's this whole thing, right? And that's how we model a character, actually. This is the input. It's the rest pose of both the bones and the mesh. And then what we assign, in addition to the vertices, so obviously all through here are all the P0, P1, P2, ... right? So all the vertices all over the place here, those are our points. So then what we want to do is we want to produce a new version of this for runtime animation that we, in our game that we want to draw the character dancing around or doing whatever. What we want to be able to do is change these transforms exactly the way we would if it were just like a robotic skeleton. So there, no mesh skinning. We just wanted to produce, say, a rotation of this thing so it can rotate upwards, like this, right? So it can bend the elbow like I was doing up there. And what we want is this mesh to come with it, right? That's what we want. Now, the equation is actually just this at its base. But there's an extra element that has to come in, and this may be why people sometimes get confused. I know back in the day when we were first working out this math, I often encountered people who didn't understand this step, and there were some really crazy things that they used to do to get around it, but you just, if you understand this step, you don't have to do anything crazy. It's very simplistic. All you have to do now is you just have to understand that you need to put things into the space of the skeleton first before you take them out of the space of the skeleton. I know that sounds weird, but I'll explain what I mean. And we'll use our elbow example so it's something you're familiar with, right? Okay. Let me say one more thing first before I explain that. So this is the rest pose. This is the input to the system. The output, right, in the game is an actual pose, right? It's something that we want to render in our game, the character animating, doing something, right? And so what we want is we wanted to go from our rest pose to some other pose, you know, of the dude, you know, running or something, right? And we want this whole mesh to go with it. Right? So as this guy's skeleton runs through the world, which is a separate problem. That's like animation. That's a totally different topic, right? But as this skeleton animates through the world, mesh skinning is the problem of how do we make the geometry for the guy follow the skeleton, right? That's what we're doing. And so what we want to do is figure out how do we go from understanding that this allows us to do this sort of blended, smoother version of the deformation that occurs if we just were to assign points directly to bones, right? How do we go from that to doing this exact operation that's what we want, right? And so there's only one trick. There's only one thing that you have to do to make this work that's not obvious from what I just wrote. Because otherwise, you just do this. Literally, you'd just do this, right? Okay, so what's the non-obvious part? Well, I said before, we start with the understanding that let's suppose we just assigned everybody to one particular bone, right? That's the non-skinned mesh case. And if we assigned every vertex to a particular bone, what do we know about how we would store that vertex, right? What do we know about that? Well, what we know is what I wrote before. This is our fundamental equation. What does it do? Well, it starts in a rest space, right? And it transforms, this is the rest space here, so maybe this point, right? It transforms one of our points by whatever the transform implies, right? That's this transform. Whatever the transform implies, I get the new point in whatever space this is now in. So if I want to take a skeleton, for example, if I want to take a transform that is in rest space, in the pose space of the guy, whatever you want to call it, the rest space is what I'm going to use, the rest space that it was modeled in, and I want to transform it, I want to transform that point out to the game, to the world space, right? Where I'm going to actually draw it. Well, what I know is that t times p gives me that if and only if p was already stored local to this transform. Right? Because that's how we normally did it in graphics. We made our cube or whatever it is centered around that original transforms point, that original, 0, 0, 0. This was 0, 0, 0. This was just the x, y, and z world axes, right? And then when we applied this t transform, we can move it out from being around the origin of the world to being somewhere else in the world and spun, right? And so if we assigned every point in our original mesh to one of these bones, what we could have done is when we wrote this skeleton out, when we took it from the 3D art package and put it into our data file format, is we could take the inverse of the rest pose, right? Because remember, now we've got a slightly more complex case. Here is the actual origin of our guy? It's down here, right? Here is a point, P0. Here is a bone, T0. Its transform looks like that in rest space. What can you see immediately when you look at this diagram? It isn't this equation, because P is not stored relative to this transform. We want P to be relative to T0. It ain't. It's relative to the rest space, whatever the space is, the modeling space of this mesh, right? But if we assigned P0 to one and only one transform, as we used to in the early days, right, we can fix this. What do? We take the inverse of T0, multiply P0 by that, and store that as our new P0, right? So what we actually have is like a P in T0 space, okay? This is a trivial process. We can do it on export. We take each individual point in our mesh. We say which of the transforms, which of our bones in the skeleton did the artist want it assigned to, and we just do the inverse transform to produce PT0. Once we have that, then this works. Now at runtime, we just do the actual current T0 times our PT0. That does give us the correct point. And that does do this operation, right? Because now we're using a point that is stored in the original space. Hopefully that makes sense. Again, that's nothing new. That's just what you do during exporting some character if you weren't doing mesh skinning. So forget character. It's just the wheel of a car, let's say, right? No character involved. It's rigid. We don't do any mesh skinning. Here's the axis system. We need to rotate the wheel of the car. What would we do? Well, we'd make all of the points of the wheel be relative to wherever this center of the wheel is. There'd be some transform there. And then we'd spin the transform and the wheel would spin. You all know this if you know non-skinned meshes, right? So this is what we would do for non-skinned meshes, and we'd just store everything relative to the transform that it was controlled by, its controlling transform. But the problem we get with mesh skinning, and the only subtlety, the only one, is that we don't have just one bone. Because what's going to happen here? Inside the art tool, the artist is going to sort of paint or adjust or use envelopes, which are sort of ways of assigning using fields. They're going to generate these, right? W0, W1. Right? They're going to generate these. And the problem is, if they're generating these weights, W0, W1, we now need to play those back at runtime, okay? And what does that look like? At runtime, we're not going to be doing that. We're not going to be doing that. We're going to be doing this. Right? We're going to be doing that base equation as many times as there are bones for a particular vertex. So if a vertex was assigned to some weight on bone T0 and some weight on bone T1, we have to do both of these transforms, right? Well, this creates a really nasty storage problem for us. It means that for every bone we wanted to use, and for some things in like this area, or the face especially, there might be 2, 3, 4, 5, 6 even bones blended together to get a final result. It starts to get a little ugly. 4 bones is not an atypical number to use as your max number, for example, in mesh skinning. Even back in my day, in 1999, when we were doing this stuff, it was already 4 was not a typical number to use, right? So this massively explodes our mesh storage, right? Because now for every point we were storing for our mesh before, we have to store 4 points, which is the transform of that point in the inverse space of each bone. So this thing we were doing before, we can do for each bone. If this was T0, T1, T2, and T3 weighted, right? So we know this point is weighted to 4 different bones because that's what the artist painted. Then we have to store inverse of each of these matrices times the point in question, right? We have to store 4 things for one input. And that's exactly what people used to do because they didn't think of anything better, right? But that's not the way to do it, and you wouldn't do it that way today because, you know, we know better. And I knew better at the time too, so I never did that. But, you know, there were a bunch of people skinning systems that worked that way in the early days because they just didn't think of something better. So what's the better solution? There's a much, much better solution to this problem. And the much better solution is to not store P transformed at all. Just store the points the way they were originally modeled. Don't transform them. So don't do the thing we would have done with the wheel. Just don't do that anymore. Forget it. P's are always stored in the rest pose space completely, so it's stored like this, not relative to T0, but relative to the total origin, relative to the same space in which T0 was modeled, right? So the skeleton and the mesh are modeled in the same space and stored in the same space, no pre-transforms. Okay? Then what we do is we compute the rebasing at runtime, and we can do this almost for free. Why can we do it almost for free? Well, look at what this equation is actually computing. PT0, what was it? Well, it was W0 times T0, the new T0, right? And I need to start differentiating these. If I wrote this out a little bit, you know, let me just write it out in the full form first so you can see exactly what I'm talking about. We need to specify our different things. So we need different spaces for these guys. So it gets nomenclature heavy or notation heavy, but it's simple in code. You just have different arrays for them, right? It's not, math gets ugly, but code stays simple in that sense. All right. So I have T0 in the rest pose. Okay. What is that? Here is the origin of my coordinate system. Here is T0 in the rest pose. Okay, so that's T0R. I need to produce a different T0 in world space, right? And that's just whatever it has to be. If I'm rotating my shoulder, if this was coming up, right, then T0 has rotated upwards, but it stayed in one place. If the shoulder is sliding out a little bit, right, then it's going to do that. If it's moving because the guy is moving, then it's going to do that. So I have a rest pose TR. This is what the modeler made. This is what the art staff made. Okay? Exactly what they made. And this is what's in the game that we're trying to produce. Okay? And what I was saying before is the old way we were doing this, right, was to say if I need to store a P0 in R, right, and I need to produce P0 in world, okay, so I'm going to start talking about P0 in world and P0 in R as well. Then what I did is I stored an intermediate value, right? I stored a P, let's call that P intermediate of 0. And what I did is I stored the inverse of the rest matrix, this guy, times that input P, right? So P0 in the rest pose times T0's in the rest pose's inverse gives me this interim value, PTI, right? And we could call it other things. Maybe we could call it PT local. I don't know, but I'm going to call it PTI, basically PT interim, because we don't actually care about it. And then I was saying, well, what we were doing at runtime to reproduce it is saying, let's take the T0 in world space, right? And we want to multiply that by our interim, and that's what's going to get our P0 in world space, right? And this was the equation we used. Well, what you actually want to do, instead of storing a bunch of these once you need to do multiple of them, is just look at what this actually computed, right? What this actually computed was T0W sub in this term. It equals that. We just said so, right? It's T rest pose inverse times P0R, okay? Now look what happens when we do the full sum. Okay? We said before what I wanted to do was extend this value. So P0 in world space is going to equal a weight, right? Some weight times T0 in world space times P0 internal plus some other thing, right? Some other weight times some other bone in world space times its internal storage, right? Dot, dot, dot. And what we would see if we substituted all of the PIs with what they actually were equal to, that we just said they were equal to, right, is actually whatever the particular bone you were talking about, whatever its inverse was, times the original PR in rest space. Same thing will happen here when I substitute in. Oops. Now what do you see, right? You see that my P0R is the same P in the whole equation. This eliminates the multi-storage problem, right? We just store W's, which is what we would have stored anyway to say what the weight is. We store the P0R once, not 4 times for 4 bones. And then at runtime, what we do is we look at this internal term. That internal term is the T in world space of any of our bones, right? Doesn't matter which one, times the inverse rest pose of any of our bones. This right here is what I call the composite matrix. I don't know if it has a real name, right? Or composite transform. That right there is the fundamental transform of any mesh skinning operation, okay? And what it is it's the transform that takes the rest pose location of something and puts it into the world pose location of something relative to a specific bone. And I can pick any bone I want, and I never have to store any additional information, right? So what we typically do in a mesh skinning pipeline, and this is absolutely crucial to understand, is we prepare the TW set. So this is like an array. We do T world space of 0, T world space 1, T world space 2, dot, 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 right? We prepare that as the output from the character animation system, or the skeletal animation system. So this is our skeletal animation system. A topic we're not covering because that's animation, nothing to do with mesh skinning. Our skeletal animation system outputs this array. It is the world space location of the skeleton. That's where the skeleton needs to go, right? Our asset pipeline, when we exported the model, right, outputs a separate array. This is just constant, never changes. This is the inverse rest pose of all of the bones, right? So we know this because it's in our file. We load it up and we just have it because it's the inverse pre-computed of these values. We know this value because we just generated from our skeleton animation system. This times this is the transform, right? T0W times TR0 inverse, right, is the final transform, or composite transform as I call it, oops, we'll put it there, of any bone. So we end up with our rendering array. And that is T0W times T0R1, 1W times T1R inverse, blah, 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 right? This is the final goal of a mesh skinning skeleton pipeline. It is the output of the skeleton animation system times the asset pipeline's inverse rest pose stored array. That produces a final transform that is just 2 matrices times each other for each slot. That is our rendering array. Once we have this rendering array, we arrive at the final operation of a mesh skinning system, and that is the skin output. And it is trivial. If we call this again, we just say it's T0C, the like composite transform. All it is just a straight readout of the points. P0 for any transform we want, for any point we want, is no more than the weight of matrix 0 times matrix 0's composite times the original point in rest pose, right? We sum as many terms of these as we want. We can support as many bones as we want and do no more work other than the one term, right? And we just go out as far as we want. This is mesh skinning. This right here is literally the points that you draw. And that's the end of it. So before our 2 hours is up, we're done. That's it. That's the system. You don't even have to know where these W0s and W1s come from, honestly, because they come from the art tool. The art tool tells you the weights. So the Euclidean one-norm stuff that I explained before is just so you understand how this equation works, but you don't even have to know how to make it because the art tool tells you the W's. They tell you the weights. Those are the vertex weights of each vertex. Now, there's a slight complication in here that's purely practical. We don't want all, because I mean, there could be 200 bones easily. There could easily be 200 bones in a modern game character. No one would bat an eyelash at that. We have the horsepower for it. You do not want to sum 200 of these terms in a vertex shader, which is where this is typically going on. Vertex assembly typically goes in a vertex shader. Why? Because you typically want to send the mesh down to the card and store it local to the card. You don't want to send the points down each time. So you send down the points with their weights, and you then just send down the bones each frame, right? Okay. So what does this look like? Well, we don't want to actually do 200 of these matrix multiplies, because what's this going to be? It's a W times a T times a P, right? This is an entire matrix transform. That's an entire 4x4 transform times an actual scalar. A lot of FMADs. We want to minimize it. So typically what we do is we say, look, we know that any given vertex is only going to be affected by a few bones at most. So we typically say, let's give the artist some fixed number of bones. Let's say 4, right? We then store the indices with the vertex. So a vertex typically consists of its position, right? Its rest position, a normal or a tangent frame, whatever. We don't care about these. Color, we don't care about those. And then finally, we have like something like a U8 or a U16, depending on how many bones you have, right? Let's say we have a U8, which is just, an 8-bit value. That is the index. And we have 4 of those. And then typically we'd also have like a U8 or something very small that is the weight, right? And so then what we do is we use these 4 weights and these 4 indices to pull out which bones we want. So we have a constant store in our vertex shader that has the TCs in it, right? I keep writing it wrong. Right? And we just use these vertex indices. We say, take the first index, grab whatever location that says. Maybe it's this one. Multiply it by the first weight. We probably encoded it as like a U8 that's just like whatever this weight is over 255, right? And that produces our 0 to 1 value or something, right? Who knows? We probably don't need to store them all because we probably know they sum to 1. If we want to, we can just store 3 of them, blah, 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 right? There's all kinds of stuff you could do here. That's minutia, okay? And that's all we do. We just compute some number of terms here. Let's say 4. We use an index to say which transforms we want. That's which bones it picks out. We use the weights that the artist specified for those bones, and off we go. If the artist specified more than 4 bones and we want to truncate, what do? We get rid of the lowest weight bones because they're the ones the artist will notice missing the least because it has the least effect on the vertex. And then we renormalize using the Euclidean one norm. Why? That prevents us from ever getting things that fall outside of the transform of those points individually, as we saw. Right? Everyone cool with that? Hopefully. Hopefully that's all clear there. That is fundamentally how mesh skinning works. That's the end of it. Right? So I don't think there's really anything else you need to know to implement mesh skinning. That's it, right? That's the end of the story for mesh skinning. But as we know, it's never really the end of the story, right? It's never quite the end of the story. Now, why isn't it quite the end of the story? Well, the reason it's not quite the end of the story is because for all of the games that this concept enabled, right? It still sucks. Go back to my original diagram. I picked elbows for a reason, and it's because they always look crappy. As I said, mesh skinning gives us something that is better than we would have had otherwise. It gives us this point. And this point, which is better than any of these points. Okay? So it's better. But is it good? I mean, it's better. A lot of games shipped on it. 90% of all 3D games probably shipped on it, right? It's better, but is it good? Okay? And the answer is no. It's not very good, right? That's not what an elbow looks like when it bends at all. So let's talk a little bit about what I guess I would call exercise for the reader, which is to say, if you understood everything that I said so far, you're in a good position to go implement your first mesh skinning system. Congratulations, do it. It's a very good learning experience. And you should be able to do something where you can maybe look at an existing file format to get you started. I think like there's some file formats that are somewhat open that have skinning data. I think maybe the Filmbox format that Autodesk pushes might be kind of open, and there's like an SDK for reading it or something. There's probably other ones out there. I don't know. So, you know, you can go take a look at that, right? You can go take a look at that. But understanding where these techniques fall short and what we have developed as more advanced techniques is very important, because that's the only way you can really take the next steps towards really high quality character animation, which games have already done for certain circumstances and certain engines, and which film definitely does always. All right. What we need to recognize here is that, fundamentally speaking, giving the artist control over where this point lies in between 2 points that are transformed as part of the skeleton is fundamentally just an approximate artistic process for what they would actually like to do. And what would they actually like to do? Well, what are they going to do when you give them this? What the artist is going to do is they're going to bend the arm around, and they're going to try and paint the weight value, which again only really gives them the ability to go between these two things. They're going to try and adjust the weight value so that it looks the least bad. That's what they're going to do, right? But they can never get something that they actually want, which is an arbitrary placement. What they'd like to do is just move the elbow and then move the point somewhere. Where should it go? Well, it should go there, right? And this is especially true with things like, you know, ZBrush or Mudbox or whatever sculpting tools people use today, where you can just paint, like sculpt vertices into position. What I'd rather do is just bend the arm, sculpt it, and then know that as I move the arm joint around, you'll just play back the sculpts that I did, right? I mean, that's what the artist wants. They don't want to have to just pick a point on that line. I mean, what does that have to do with anything? And furthermore, it doesn't model the problem at all either. Skin is wrapped around, first of all, skin is itself somewhat elastic, but it's wrapped around fat, which, you know, slides and deforms. Muscle, which grows larger, actually, right? If you tense a muscle, it will expand. And then only that internal bone itself, the actual physical bone you have, really stays, for our purposes, rigid. Everything else is very deformable. And so it doesn't make a lot of sense to tell the artist, pick some rigid line that's going to transform in between these two effective transforms that would only really correctly model a literal skeleton, like a literal series of bones. It would work just fine. But it would not work at all for the fat, the skin, and so on. And so there are two camps, two fundamental camps that these fall into. And one is just, I guess I'll call this double down, right? There's the double down camp and there's the simulation camp. And I should say that they're not, much like all of the linear blending, they're not mutually exclusive. You can be somewhere in the middle. I'll tell you what both of them are. We're going to take simulation first because it's the least interesting from a game perspective, because you really just don't do it very much. The simulation perspective is, oh, well, instead of doing mesh skinning at all, let's actually have some really complex set of things that model surfaces and will attach the points to those, right? So the simulation approach says, all right, I'm going to actually pretend there's a real bone, like for reals, made of like marrow and stuff, right? And then I'm going to actually say that there's like muscle fiber, like wrapped around it, like for realsies, right? And then I'm going to say that there's a fat layer. And then I'm going to say there's actual skin. Like, I'm literally going to do all of that crap, right? And then when I move this joint, I'm going to actually do finite element solves, or something, to figure out how this skin will interpenetrate, how the fat will bulge together, how the muscles will contract. I'm going to simulate, if I pull it this way, that the bicep is going to bulge here, right? Blah, 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 blah. Fundamentally speaking, this is the route you want to take if what you're trying to do is put as much programming in as possible and the least art, right? Which you may want to do depending on your goals. You may want to go a programmer-heavy route, and that is simulation. Just like everything else. The more simulation you do, the less art you need, kind of like how physics removes some of the need for animation, because you can just simulate what you're trying to do, right? But it removes the art from the process. It's not very artistic. It's not very controllable because it's a simulation under the hood. Just like physics makes it pretty hard to produce animations you actually want. You have to sit there and fuss with them a lot, and we spend a lot of time figuring out how to move them more towards the artistic side of things, right? So it has some drawbacks, but it has some strengths. And the biggest strength it has is maybe it can produce, once you do it once, maybe it can produce a lot of useful animation results for you without an artist having to be there to adjust them. Now the double down camp is to say, let's go the artist route. They were already modeling everything using tools. They already built the skeleton themselves using tools. So let's just give them tools to do more work here. And so what they do in the double down camp is exactly what I just said. Let's have the artist sculpt more, right? Artist sculpt more. You know what I'm saying? So basically what we do there is we say, all right, the artist is going to give us a rest pose. Yes, that's like whatever the arm looks like when it's just out. But then you know what else they're going to do? They're going to pose the arm in like an arm up position. And they're going to model the bicep bulge, right? And then they're going to rotate the arm over, and they're going to model that. Okay. And so with this camp, what doubling down on art input does is it said, let's have the artist give us lots of examples. And then what our job's going to be is to change those blending equations to be able to reproduce as closely as possible all of the examples that our artist gave us by driving which samples we use off of the position of the underlying skeleton and any other parameters they want to give us. For example, we could have a stress parameter that you specify for each bone that is how taut the muscle is, right? And so the artist can crank up the stress. Is the dude like really, flexing his arm, or is he slack, right? Because I can do that with my arm, or I can do that with my arm, right? And you can see that the bicep, totally changes its shape, even though the skeleton hasn't changed, right? And that's how much stress, is being put through there. So we extend the parameter space of the skeleton to include both bone positions and rotations as before, but we also include in that set, we also include sort of scalar, or I shouldn't say scalar, but other parameters, right? They could be anything the artist wants. And what we do when we look at these systems is we take an input mesh plus the set of bone positions and parameters that the artist said it correlated to. And we typically use what is known, well, I don't know if it's known, this is maybe my term, but we use a reduction process or a fitting process to take a large number of examples and produce smaller blending equations that still look almost exactly like the ones I already drew, but just with more terms, that we can compute at runtime given a set of these to produce an output set. Okay? Reading more about this, I would highly recommend the paper Pose Space Deformation by Industrial Light and Magic. It is probably the easiest one to understand, and it was an early one in the field, so it's pretty basic. And obviously, we've done way more complicated stuff since then, but I would recommend that one. To give you a link, this is it. Maybe, is it it? All right, maybe it wasn't by Industrial Light and Magic. I don't know what Centropolis is. Why did I think this was post? All right. Well, I have no idea what Centropolis is, so never mind. I thought it was Industrial Light and Magic, but I'm wrong. I guess it's this. All right. I apologize, Centropolis, for misattribution. Anyway, I think that's probably the easiest paper. It does involve some matrix fitting, which we haven't covered here, and is kind of a topic for a different time. It's its own topic. So I'm going to end it here, where we perfectly fit this into our window, which is pretty crazy. But I think I've covered pretty much everything you need to know to get started on mesh skinning. If there's anything I left out, I'm sure we can cover it here in the Q&A. So hopefully that pretty much is that. I'm going to pop the Q&A here and see if anyone has any questions on topic to this. Please let me know. For what version of Granny had I worked? I did all of the versions up through 2.7, maybe? 2.5? Hold on a second. Okay, so I did all of the versions prior to 2.4. Is what I did. Yeah. So I think all of the versions, so 2.3 was my last full version I did, and somewhere in between 2.3 and 2.4 I think was when I handed it off to Tom. And I did all of the previous versions. Starting from 07B, which was the first release, all the way through. Are the bone transform inverses stored relative to the mesh center? Yes, generally speaking. The idea is that you want to pick a single space in which you store all of your source data. So you store the entire mesh and all of the inverse transforms. You store those all relative to the original single model. Oh, Molly's asleep right now, but I'll let her look out the window later. Sorry. What file format would you recommend for beginners and for someone not willing to use a lib? So OBJ files are the easiest files because they're just a text file that's obvious what the stuff is. But my problem with them is I don't know if most art tools will export a weight section for you or not. So if you can get an art tool to output an OBJ file that has vertex weights, that would be a good way to start. But I just don't know. So my problem is I'm not sure what file format would be best to start in because I don't know which ones have weights. When I started Granny, there were no exports with weights. Granny has its own exporter that you run inside the art tool to extract the information. It doesn't use an existing file format. Would Bezier curve work for the fatty part of the arm? Probably be terrible. Bezier curves don't work well, but they have been tried. There was a package called I think it was called Character Studio. So there is a plugin for the original 3D Studio Max, the very first version of 3D Studio Max, which isn't the first version of 3D Studio because 3D Studio actually went up through version 4 at least, possibly 5 in DOS. So when they ported it from DOS to Windows and made 3D Studio Max, there was a thing called Character Studio, which was done by was it done by Glacier? I don't know who did it originally. I don't remember. But Character Studio featured a thing called Biped, which was a little like intelligent skeleton that did some things automatically for you. Kind of crappy, but it was better than most things at the time. And then Physique, which was a mesh skinning tool. And the way that Physique worked was it actually threaded a Bezier curve through the bones. It doesn't really help much. It's not great, but it's something you can look to if you want to know how that works. I wouldn't recommend it. How often would composite bone matrices usually be updated? Per frame. Yes, per frame. So every frame, what you do is you compute the results of your animation. That gives you a new world space transform for each of your bones. You multiply in the inverse that you stored in the file, and every frame you do that combination to give you your final world transform. How do quaternions fit into this? They don't. So quaternions really have nothing to do with any of the stuff that I've talked about. Quaternions are traditionally used in animation to represent the rotations of bones, but that's purely a storage format, or it's not really a storage format, a manipulation format that can get you some benefits, right? There are things called, what the heck is it called? There is a thing called dual quaternion skinning. And that is basically a sort of a separate technique for skinning that, you know, I, I haven't implemented this personally. It came out much well after I was done with working on Granny at all. Um, you can take a look at this if you're interested, but it it's really, I don't know how. I don't have a strong opinion about it because since I haven't done it myself, I don't know how much you would really care. I think it's kind of something that's not probably particularly necessary because you want sculpted results. You're really not trying to fix artifacts like this in the real world. You tend to just add more artistic sculpting to the process. But that's one place you can have quaternions involved directly in the skinning process. But that's a special case and isn't really necessarily a general idea about mesh skinning, if that makes sense. What kind of skinning do we use for Handmade Hero? We don't really do skinning in Handmade Hero. We covered this just because I wanted to cover it because people had asked. How do you recommend to go about learning a new language or technology? That's not a little off topic for this stream. You probably want to ask that on a different one. Did you miss Live Chartreuse? No, Roman, you did not. I have not played Chrono Trigger yet. I'm kind of waiting for it to be on sale. And my Chartreuse is still almost full. Maybe this week we'll do some Chartreuse gaming. It might not be Chrono Trigger because, like I said, I was kind of waiting for it to go on sale. I have it on a wish list. But if you send a lot of data to the GPU and it doesn't have that much memory, is there some sort of virtual memory that it will be used, or will it crash? So typically speaking, that depends a lot on what API you're using, and also the answer is generally yes. Nowadays, there is some sorts of virtual memory happening there. But even in the old days, there was kind of some virtual memory in the sense that the driver would actually manage it for you. So you kind of didn't know, but behind your back, it was swapping memory out. So that's a topic I don't really want to cover on this because it doesn't really have anything to do with mesh skimming. But the answer is, to a certain extent, yes. To a certain extent, no. And it depends on which card and which driver you're talking about. So the lerp versus slurp is in the animation system and not on the skinning system. That is correct. The skinning system does not fundamentally care how you are producing the points. The skinning system is just that inverse transform and then a weighted blend. How you're producing the actual transforms forward in space is completely up to you. So the skeletal animation system is the part that cares about lerping versus slurping. The mesh skinning never needs to do anything with slurping. That's just unnecessary, as far as I'm concerned. It's not to say you couldn't engineer one that did it. And that dual quaternion skinning is kind of an example of someone saying maybe we should be doing more rotational things inside our skinning system. But the basic skinning systems that form the foundation of most games even today just fundamentally don't do... They don't use things like quaternions to produce the final blend weights, to produce the final blend points. Typically, you're using quaternions to produce the interim transforms that you use to then do the blend equation. And again, with the caveat that things like dual quaternion skinning do exist, so some people do go kind of a different direction with it. There's not like a right answer. All right, I think we've pretty much got all the questions. I don't see any more in there. So I think we can safely wrap it up. Quick check. Does anyone have any questions that are about mesh skinning before we close up? Roman asks, coordinates you've drawn Z is up while OpenGL is deep. So this is kind of an interesting, I'll quickly say this briefly since we don't have any questions that are totally on topic, and this is somewhat on topic. I will just go ahead and do this. So it's worth noting that saying that OpenGL has Z is up while OpenGL Z is deep is kind of a misnomer. And let me tell you why. I think of this as similar to the mirror analogy. A lot of people are like, why do mirrors reverse things left to right instead of up and down? And the answer is they don't. They reverse them, period. And whether you think of it as reversing them up and down, or whether you think of them as reversing it left to right, is really because of how it's happening in your head, not because of how it's happening in the world. The same is true here. So in your head, what you're thinking is, well, my computer monitor is obviously situated like this. I hung it, on a monitor stand or something, and I am a human who looks forward at this monitor. Therefore, when I'm using OpenGL, because its coordinate system aligns this way, that's the Z, right? And that's the X, and that's the Y. Ergo, in OpenGL, Z is this, it's looking backwards, basically, not quite forwards, it's actually the backwards vector, right? And that's because you applied a whole bunch of human-specific stuff to your thinking about it, right? How you tend to put a monitor up, right? What you expect that monitor to show, how you expect to sit in front of the monitor. But in reality, I could put the monitor anywhere. I could put the monitor like this, and I could have a chair with a sling in it, and I'm hanging over the monitor like this with my arms out like Superman, looking down at the monitor, right? And the monitor is sitting on the floor. At that point, what is OpenGL's coordinate system? I ask you, right? Well, oops, let me just draw it 100% correctly to the diagram. It's that. And that is Z is up, right? Z is up. It points upwards. So really, all you have to do if you want Z to be up and X and Y to be the world plane, which you can if you want to. It's up to you. Who knows? If you want Y is up, Z is up, it's your choice. Is just say, when I start out, what am I looking at? Am I looking at something, do I expect my startup to be an FPS or an RTS? If it's an RTS, I start out looking down at the world. That is Z is up, right? If it's an FPS, then I start out looking out at the world, and that is Y is up, right? In OpenGL native coordinates. You know what I'm saying? So I just choose the RTS paradigm. I choose when I turn on my monitor that I'm looking down at the world, right? Like an RTS, instead of looking up at the world, we're looking out at the world like an FPS. Does that help at all, Roman? El Spacel says the ligament seems to have a bearing on the arm movement. Also, the pivot of the arm, knee, shoulder seem to be on the outside and not the center, which makes me think we are thinking about the problem naively. Who knows? No, you're correct in your observations, and a lot of times artists will do that. So if you look at where they, place the bone, even in a naive mesh skinning system, they will often put it like towards the outside so that when it bends, it produces a better result. So you're not wrong, and artists will do that. For sure. And that's just about getting a better base result before you ever sculpt anything. Roman says he's in Redmond if you want to use that chartreuse. The chartreuse is for me trying to play Chrono Trigger when I'm a little bit tipsy. Brian, greetings, Casey. I've been going through the multi-threaded code. Remember the one episode you were talking about loading the asset files in chunks? Okay, that's kind of off topic. So let's do that for what stream let's do that on a regular stream. Following on from what you've explained about coordinate systems in OpenGL and how we choose it, what do we need to do to set up Z up instead? Again, trying to just underscore this, it already is. It's just what your mind thinks of the default camera position, right? If you want Z to be up, all you have to do is think that a non-rotated camera points down. That's it. Now Z is up. It's just a change in thinking. You don't have to do anything else. You don't have to do anything. It's just how you think about your camera. That's it. Your electrostorm yesterday made national headlines. Yeah, it did. All right, I'm going to go ahead and wrap it up because we're done with our stream today. Thank you, everyone, for joining me for the episode of Handmade Hero. It's been a pleasure blackboarding with you, as always. I hope that gave you a pretty intuitive understanding of all of the components of the mesh skinning pipeline. If it didn't, I apologize. Hopefully, you can look to some secondary resources or drop by Handmade Hero sometime, handmadehero.org. You can always go to the watch page, and when it's not live, it will have a schedule on there saying when it is live, so you can always stop by and ask questions, and we can cover anything that you might not have understood about this introduction to mesh skinning. I always take questions during both the pre-stream before we start and also the post-stream Q&A, so you can come by and ask those questions. That's it for today. I'll be back here either sometime this week if I'm feeling saucy, or next weekend with more Handmade Hero, where we will be putting our new lighting sampling spheres into effect. That hopefully you'll join me for. Until then, have fun programming, everyone, and I'll see you on the internet. Take it easy, everybody.